Yes, so my name is Will Klieber, and I will talk about automated code repair to ensure memory safety. So software vulnerabilities constitute a major threat to DoD, and memory violations are among the most common and most severe types of vulnerabilities. For the past 3 years, memory vulnerabilities have constituted 15% of the CVEs in the NIST National Vulnerability Database and 24% of the critical severity CVEs. Earlier this year, a vulnerability was discovered in the iPhone iOS that allowed an attacker to take control of a phone when the user visited a malicious website. This vulnerability was exploited by the Chinese government, according to TechCrunch. A similar vulnerability was discovered in the Android stagefright library in 2015. A vulnerable phone could be compromised just by receiving an MMS message specially crafted by an attacker. The Cloudbleed incident of 2017 is interesting because there is no active attacker. Rather, the Cloudflare web proxy had a vulnerability where, under certain conditions, it would read past the end of a buffer and reveal potentially sensitive information to unauthorized users. There is a huge volume of code in use by the DoD, and that code has an unknown number of security vulnerabilities. So what's our solution? What we propose is to automatically repair source code to assure memory safety. What we would do is we would insert code to check to see if the program is about to commit a memory violation and to abort the program when that's the case. And that would prevent attackers from exploiting the program. In our approach, we transform the source code first to an intermediate representation, and we retain the mapping from the IR back to the original source code. We then try to assure that each memory access is both within bounds, which is spatial memory safety, and that it's not to a deallocated region, which is temporal memory safety. So far in this project, we have focused on spatial safety, and next year we will also address temporal safety. So if we are unable to assure that the program is already memory safe, then we will attempt to repair it to make sure that it is memory safe. To do this, we will use fat pointers to store bound information where possible. We will then map the repairs that we made at the level of the intermediate representation back to the original source code. As input, our tool takes a buildable code base, and as output, it produces a repaired source code base. And that repair that we produce is suitable for committing back to the repository. So it's not only just source code, it's human readable source code, something that people can continue to work with. So we currently support C, and we plan to have limited support for C++ in the future. And this is year 2 of a 3-year project. So we envision our tool being used before every release build and occasionally for debug builds. It's intended for ordinary developers and does not require any special knowledge of static analysis. It can be used as part of a tool in a DevOps tool chain, and it can also be used to be applied to legacy code. So what about false positives from static analysis? Reducing the false positive rate is difficult, but it turns out that we actually don't need to reduce the false positive rate. And that's because it's okay if we repair false positives as long as we don't break the code. Now, there will be some overhead that we introduce by these bounds checks, but we expect that it will be low enough that it won't be a major problem. So why would you want to do repair at the level of source code as opposed to a compiler pass? There has been a lot of existing research that does repairs at the compiler pass, but there's a few reasons why people might prefer to do it at the level of source code. One reason is that repairs at the source code are easily audited, whereas with the compiler pass, you basically have to trust the tool. Secondly, repairs at the level of the source code can easily be tweaked to improve performance if necessary. And many programs have a very small performance critical core. So if you need to manually adjust that small core, it isn't nearly as much work as manually repairing the entire code base. Third, repairs at the source code are frequent and easily handled, whereas changes to the build process are more difficult and error-prone. And in fact, some projects use a compiler specific to their hardware. So if you develop a compiler pass for one compiler, well, then it doesn't help that project. Fourth, it's okay if we do slow heavyweight static analysis for source code repair, because with source code repair, we produce a persistent artifact, so we do not need to regenerate that every time we recompile the program. So there is a gap between static analysis to detect bugs, which works best on an intermediate representation, and repair on the original source code. The difficulty is that we must map the changes that we make at the IR level back to the original unpreprocessed source code. So to address that gap, we use the source code repair pipeline shown on this slide. In step one, we parse the source code, and we produce we parse it into an AST and an abstract syntax tree, and we retain the source AST mapping. And specifically, we annotate each AST node with the corresponding range of the original source code text. In step two, we take the AST and transform it into our intermediate representation. And again, we annotate the IR with information of how to transform it back to the AST. Then in step three, we perform our analysis and repair on the intermediate representation. Then in step four, we take the repaired intermediate representation and transform it back to an abstract syntax tree using the annotations. And step four is semantics preserving by construction. We always preserve the semantic changes that we make to the IR. In step five, we take the repaired AST and translate that back to the source code level. And if we modify an AST node, well, then we generate new source code text from that modified AST node. But for an AST node that is not modified, we just reuse the original source code text. So our main way of repairing the source code is to use so-called fat pointers. A fat pointer is a struct that includes the pointer itself as well as bounds information. And before dereferencing a fat pointer, we perform a bounds check. And if the bounds check fails, then we abort the program. So for each pointer type, we introduce a fat pointer struct that has three fields. The first field, RP, is the same as the original raw pointer. Then we also have the base of the memory region and the size of the memory region in bytes. So fattening of pointers has previously been done as a compiler pass, and in this work, we extend it to do the repair on the source code itself. So here's an example of a program with a pointer P that points inside a string. When we do the repair, P becomes a struct, a fat pointer struct, and the raw pointer component is the same as the original pointer. The base points to the beginning of the memory region, and base plus size minus 1 points to the last byte of the memory region. So here we see an example snippet of code and the output that our tool currently produces for that snippet. So on line 7, we can see that it changes the char star pointer to be a fat pointer, and it wraps the call to malloc inside this wrapper function fat malloc, which basically calls malloc and then just returns the corresponding fat pointer. On line 10, we insert a bound check before the pointer dereference, and then on line 11, we just change the pointer arithmetic to work on fat pointers. So this fat malloc wrapper function is pretty simple. We just call malloc with the given size and then assign the result to the raw pointer component and the base component. size of the fat pointer is the size requested, except if malloc returns null. If malloc returns null, then we set the size component to 0 because we allocated no memory. So for fat pointer addition, it's real simple. We just add the given integer to the RP components of that fat pointer. And this can either be defined in standard C using a function for each type, or we could use a macro using C extensions or the C11 generic feature. The advantage of the macro approach is that the name of the function like macro is shorter, so we clutter the code base less, but it's less portable, so there's a trade-off there. And we let the user pick which of these they want to use. For bound check, this function just checks to make sure that the pointer is within the bounds. If it's not, then we abort. Otherwise, we return the raw pointer. So many programs have data structures such as linked lists and trees. Now, if such data structures are accessed by external library code, then we cannot fatten those pointers because the external library depends on the original memory layout of the program, and if we fatten the pointers, well, that changes the memory layout. So to identify those pointers, we use a whole program points to analysis, and specifically we use an allocation site abstraction. And then we just mark those pointers as being ineligible to be fattened. So we cannot assure memory safety for those particular pointers. But we also don't break the program. The program still works even though it links to these external libraries. We just don't get to give as strong as a memory safety proof. And we're also working to investigate techniques to analyze and repair x86 binary libraries, which would allow us to do the complete repair even in the case of external libraries. So, as I mentioned on the previous slide, we cannot guarantee safety in the presence of external libraries. We also can't guarantee safety in the presence of non-standard pointer tricks such as XOR linked lists if the program reuses memory for different types, except via unions, which we do support, dynamically loaded code, including JIT, or basically anything else that interacts poorly with fat pointers. So concurrency is also an issue because concurrency can lead to race conditions which cause memory corruption regardless of whether the program would otherwise be temporally or spatially memory safe. So now I would like to just talk briefly more about this step 5 of how we take the repaired AST and how we convert it back to original source code. So we implemented a modification to Kling to extract the source AST mapping, and we use that mapping to translate the repairs done at the AST level back to the source code level. In doing so, the C preprocessor is our main source of difficulty. So if we need to make a repair to a macro use, well, in general, what we do is we make the repair to the expansion of the macro, and then we just replace the macro use with its repaired expansion. However, if we only need to make a change to an argument of the macro, then in some cases we can just change that argument and leave the macro use unexpanded. For repairs to included code, we just repair the included file. And if conditional compilation directives such as #ifdef occur inside an expression, then we just need to be careful that we don't obliterate those preprocessor directives if we happen to rewrite the code. White space, for example, if we insert a statement, it should be indented to match the surrounding code. When an expression or a statement is repaired, well, then we generate a new source code. We generate new source code from that repaired AST, but if a child AST node is unchanged, then we just reuse its existing code. So the C preprocessor can conditionally include or exclude pieces of code depending on the configuration that's chosen at compile time. And examples of options in a configuration include the target platform, Windows or Linux, including or excluding features, for example, FIPS mode on OpenSSL and debug versus release mode. So the final repaired source code should be correct under all desired configurations. However, most static analysis tools, including applying, work on a single configuration at a time. So what we do is we just repair each configuration separately and then merge the results in such a way that guarantees that the merged result produces the same semantics as it would under each individual configuration. So here's an example of how we merge repairs for different configurations. So in configuration 1, the symbol useLong is defined, so we replace the long star pointer with the fat pointer. In configuration 2, the symbol useLong is undefined, so we repair the int star pointer. And then we merge those two repairs together to get a final result that is correct under both of the configurations. So we say that an operation is idempotent if applying it multiple times gives the same results as applying it just once. So we would like our repair operation to be idempotent. If you repair a code base and then you do the repair again, it should have no effect because the code base has already been made memory safe. So unfortunately, we are not there yet. So what we do to avoid doubly faceting things is to introduce this defatten operation. It takes a repaired code base and changes all the fat pointers back to raw pointers. Then we can apply the repair operation again. And that composition of defatten and repair is idempotent. So this project has been a team effort, and I would like to acknowledge all the members of the team, including Ryan Steele, Matt Chirella, Derek Lung, David Svoboda, Mike McCall, and Ruben Martins. So in the near term, we are adding features and fixing remaining bugs to handle the spec 2006 benchmarks. We expect by the end of January that we will have our tool working for spec as well as lots of other real-world programs, with the caveat that we might introduce performance overheads of at least a slowdown of, or at most a slowdown of 2x. But even then, slowing the program, making it be twice as slow, might not be acceptable in many cases. So that brings me to bullet point number 2. We are also optimizing the repair to remove unnecessary bounds checks and patternings, and we expect, hopefully towards the end of the fiscal year, we should have the overhead down to around 10 to 20% for typical programs. And we're also working to store the bounds information in shadow memory and address temporal memory safety. And we will be working with our DoD transition partners to evaluate our tool for DoD use on real programs in use by the DoD. In the midterm, we hope to extend this approach to handle other types of repairs, as well as increase the level of automation. We also foresee DoD programs and contractors using this automated repair technology to remove spatial memory bugs from both legacy code as well as from new code in the development pipeline. In the long term, our tool can be used by DoD to ensure memory safety, both spatial and temporal, as part of all software projects with code that is written in unsafe languages, such as C and C++. And that concludes my talk. Are there any questions?
Do you have any estimate about what kind of overhead these checks require?
Yes. So in the worst case, the worst case is probably something like where you have a singly linked list where almost all of your data is pointers. So that would incur a 3x memory overhead. And I also did a performance test on that, and that increased the runtime by a factor of 2. So it was twice as slow for that. I also did another test where you just walk through an array, and that gave you a 20% overhead.
One question I have is the strategy to deal with memory vulnerabilities. There is the approach of using a moving target defense, like polyverse. Did you trade those different strategies versus repair and all the issues that come with repair?
Yes, so I would say in general, the best defense is a defense in depth. So you would ideally want to apply all the strategies that you can. So making repairs is good, but you also might, I mean, this approach should address all the memory vulnerabilities, but there might be a problem, or like there might be some cases like if you have an external library where we won't catch a memory vulnerability, and in that case you would need to use other techniques as well to ensure safety, yes. Does that answer your question?
I had a question. Do you have a feel for how many memory problems can be found with a static analyzer versus those that can only be found with a dynamic analyzer?
So in general, with static analysis, there's a trade-off between false positives and false negatives. If you want to, you can easily make a static analysis tool that gives you no false positives, but at the expense of many that gives you no false negatives at the expense of many false positives. So there is that trade-off. So in terms of a practical static analysis tool, you probably can't find everything because you would get an unacceptable number of false positives. So I would say there are some cases where you can get better results by using a combination of static and dynamic versus just one or the other.
Yeah, I was thinking of C++ function pointers. You don't know where they point until you're executing.
Right, yes. So that would
like
be
that.
yes, so that would be a major source of false positives if you want to eliminate all false negatives, because you would need to consider it pointing to whatever it possibly can, and that would lead to a wild explosion of false positives, yes. Can you implement Spec 2017? Yes. Assuming, yes, we should be able to do that. The reason why we're working with Spec 2006 is that we already have them. There won't be any technical issues with us doing Spec 2017.
I guess I had a couple of questions. Maybe one observation and a question, I guess. How do you define memory safety of your programs? It seems like you're following these pointers through sort of these nested hierarchy. Is memory safety, your definition of memory safety encompassing every possible pointers that can be reachable from this module that you're evaluating, or is it just the module sans any of the external calls that the module does? I guess my next question is sort of playing off of that, which is, have you tried to sort of explore these two alternatives and seeing whether maybe constraining the module in some way to just say, I'm not worried about the external calls that this module makes, but I'm only worried about whether this module in itself has, is trying to sort of override some other piece of code or data otherwise?
Right, so yes, a very good question. So the way that we define memory safety, at least for temporal memory safety, is that whenever you allocate memory and you get a pointer there, any pointer derived from that allocation must stay within the allocated memory region. And that also fits the C standard, where technically it's undefined behavior if you don't do that. If you take a pointer, if you have a pointer to some allocated region and you drive a pointer outside of that, that is undefined behavior according to the C standard. So that is what we use as our definition for memory safety for spatial memory safety.
If that be the case, have you looked into abstract interpretation techniques which will might help you reduce this false, or maybe even eliminate them in some instances?
Yes, that's what we're planning on using. Yes, abstract interpretation is what it would probably be our main tool to eliminate the false positives, yes.
Okay, sounds good.
Thank you.
Thank you.